In the last video, I suggested that there were some problems with the Bohr model of the atom. Even though it worked well when it was first conceived, eventually people started to realize, like most scientific theories, that it had some shortcomings. So we're going to look at what those shortcomings were and what the response was that developed into the current model of the atom that's based on waves rather than a particle view of matter. People initially realized that there was a problem with Bohr's atom because the calculations worked really well for hydrogen. Remember, Bohr calculated using classical physics what colors you should see in the line spectrum of hydrogen. And all of his calculations worked out right. You got exactly the colors in the model atom that Bohr developed that you actually saw in the line spectrum. But when people tried to apply this to other atoms than hydrogen, it just didn't work. And at first they thought they were just doing the math wrong, or that they needed slightly more complicated math. But that really wasn't the case. It just never worked except for hydrogen. One big problem with the Bohr atom was that it was based on a particle idea of what the electron was. And Louis de Broglie was able to show that electrons really don't behave like particles all the time. In fact, in many cases, electrons show themselves to us in a fashion that makes them look like or behave like waves. Now, there's still sort of a way to make this work with a Bohr-like model. You can see this picture here shows some wave functions imposed on what look like orbits. So the blue circles here are Bohr's orbits, and the dotted red lines represent these waves. And the waves will oscillate back and forth between two different positions. So, like, we'll say this wave here, in one position it's as it's shown, but then it'll shift to this position and it'll oscillate back and forth. Or the wave that's at orbit number 2 could be in these two different positions, so it'll shift back and forth between these two positions. And orbit number 3, well, you've got, more lobes to this wave, but it would function in much the same way. Here's another way of thinking about it. As the light energy enters the atom, you can see the atom shifting to different wave forms. The electron isn't really a particle moving to different orbits, it's just taking different forms of a wave as it reaches these different levels. That's kind of de Broglie's idea. You have to think about it as a wave, not as a particle. Another big problem with the Bohr atom that went beyond just de Broglie's idea that things have to be in waves was when Werner Heisenberg, another physicist, showed how it's not possible to know two things about an electron at the same time. One is where it is, and the other one is where it's going. In other words, you can't know its location and its direction at the same time because the very act of measuring it actually changes it. One slightly inaccurate way of visualizing this is, imagine that you're playing baseball and you're in the field. The pitcher pitches the ball in and the batter hits it, and the ball comes out in your direction, so it's your job to catch it. How do you do that? Well, you have to get underneath the ball and then get your glove up and catch it. How do you know where the ball is going to come down? Well, you sort of guess, but you gather information to make that guess. You look at the ball, you see where it is, and then you take a snapshot. Your brain takes a snapshot a fraction of a second later and sees where the ball has moved to. And then it does it again, and then it does it again, and your body starts to respond after your brain figures out the trajectory by looking at all these snapshots, and you start to move to where the ball is coming down. Now pretend you're playing an electron ball. Pitcher pitches in the electron, batter hits the electron, and the electron comes flying up into the field where you are. So it's your job to catch the electron, and you find the electron, and your brain takes another snapshot a fraction of a second later, and then you look at the electron again, and it's not anywhere close to where it was going. And then you look at it again, and it's in a completely different part of the field, and then it's behind you, and then it's back at the batter again, and then it's way over on the other side of the field. What's going on? Well, for a baseball, we gather the information by the light that bounces off the baseball. Think about this. If you're playing a night game, the only way you see the baseball is by the lights that are shining on it. If someone shuts the lights off in mid-flight, you are not going to catch that ball because you don't know where it is anymore. Well, with an electron, you detect the electron the same way. It's not with visible light, but with wavelengths of electromagnetic radiation. When they hit the electron, however, they don't just bounce off. They bounce off and they change the path of the electron because the electron is so tiny. Here's another possible way to understand this. Here's a blindfolded person in a room, and this ball is flying towards them. They know how fast it's going, but they don't know where it is until it hits them. Once it hits them, they know where it was, but at that very instant, the act of figuring that out changes where the ball is going. That's Heisenberg's uncertainty principle. Not exactly, but it's a kind of an easy explanation to understand. So what's the response? Well, a man named Erwin Schrodinger started out from the idea that electrons behave like waves. He incorporated de Broglie's new understanding into trying to build a model of the atom. The other thing that he did was he incorporated Werner Heisenberg's uncertainty principle into his idea and said, let's not even try to say where the electron is or where it's going. Let's just use a kind of a statistical method to try and figure out where the electron is likely to be found. Now, Schrodinger was particularly well suited for doing this because he knew a lot about waves, and he knew that waves were quantized. And that's a very important part of where his starting point led him to. Imagine you have a string, like a guitar string or a piano wire, stretched between 2 points, and initially this string is at rest. Now, once you pluck this string, there are a number of possible ways it could respond when it vibrates. However, what Schrodinger knew is there's a pattern to all these modes of vibration. If the length is L, the total length of the string, in this first wave formation, you have half of a wavelength. A wavelength is going up, down, and back again. So that would be one wavelength. But in this first mode of vibration, you only have really half of a wavelength because it goes down and up, but it doesn't go up and down again. And so we could say that a wavelength is 2 L's long. To fit an entire wave in, you'd have to go a whole nother length. In the second mode of vibration, we have a wave. We have down, up, up, and then back down again to the resting point. So we would have 1 L is the wavelength. In the third mode of vibration that we have, here's one wavelength to there, and then there's another half of a wavelength. And so a wavelength is actually 2/3 of L. And in this fourth mode of vibration, here's a wavelength to there, and then there's a second wavelength until you get to L. And so this is actually 1/2 of a wavelength. Now here's where the pattern comes in. I can rewrite these a different way. 2L is really 2L over 1. And L is really 2L over 2. And 2/3 L is really 2L over 3. And 1/2 L is 2L over 4. So here's the pattern that's developing. In all cases, we have 2L divided by an integer. And that integer just keeps getting bigger for every mode of vibration. And there really aren't any other possible modes of vibration because the string is fixed at both ends. It has to have a node. It has to have a 0 point there, and it has to have one there. And that restricts how many possible wavelengths you could get. So we could come up with this general pattern. We could say that the wavelength is equal to 2 times L divided by N, where N is equal to 1, 2, 3, 4, all the possible N's that you want, all the way up to infinity, but they have to be integers. Well, that means that waves are quantized. And Schrodinger can make a connection because the energy of electrons was also quantized. Remember that Bohr found that you could be in one orbit or a second orbit or a third orbit. Or de Broglie saw that you could have one wave or a second waveform or a third waveform, but you couldn't be in between. So the energy of electrons is quantized, as seen by the line spectra. Waves are also quantized, and so there should be a way to make a electron wave equation like we made a string wave equation in the last slide. Well, our one-dimensional waves were described with one quantum number, n. Remember, the equation was wavelength is equal to 2 times L divided by n, where n was equal to 1, 2, 3, and on up to infinity if you wanted to go that far. Electron waves are three-dimensional, and so three-dimensional waves are going to need 3 quantum numbers. So we end up with 3 quantum numbers, n, L, and another one called m sub L to describe the three-dimensional wave. Now the math behind this is extremely complicated, and We're not going to go into the details of this math because you wouldn't understand it anyway. However, we can skip ahead to the conclusion that was eventually reached after Schrodinger and some of his colleagues worked with these equations and tried to give them some physical meaning. And we're going to slip back to the particle model of the atom to give it some more understandable character that we can use to understand chemistry a little better. The bottom line is, in the Schrodinger atom, in the wave model of the atom, there are these things called orbitals. Not the same as orbits, but orbitals. Orbitals are not really a thing. They're just a region in space, a three-dimensional region where an electron is likely to be found. The electron doesn't have to be there, but that's where you're most likely to find it. And it's not a very small pinpointed space. Compared with the atom, it's a pretty large region. And somewhere in there, if you're going to collapse the wave and view the electron as a particle, that's probably where it's going to be. No orbital ever contains more than 2 electrons. So an orbital is a region of space that contains 1 or 2 electrons, but no more. And this is kind of how it's organized. I can have an orbital, or 2, maybe 3, and those orbitals might be inside of a unit called a subshell. So a subshell is a group of orbitals. So these are individual orbitals. And subshells, there could be more than one of them. Here's another subshell that has only 1 orbital in it. Here's a subshell that's got 5 orbitals in it. All of these subshells could be part of a shell. So the organizational structure in an atom has shells, more than one shell. Each shell has subshells, and each subshell could have 1 or more orbitals in it. That's the basic structure. Now there are some rules about shells, subshells, and orbitals, and we're going to go through these rules and develop a way of understanding where the electrons are or are likely to be found in atoms. First of all, let's assign some meaning to these quantum numbers. N is called the principal quantum number, and this is its range. This is like Bohr's N, or this is like the string wave N. Its range starts at 1 and goes up through integers and could go all the way up to infinity. But it can only be integers, it can only be positive. So no 1.5, no -2. What's its meaning? Its meaning is what shell is the electron in. And in general, the larger the value of N, the farther that electron is from the nucleus, on average. Although we don't really know where the electron is, this is just sort of an average position of that electron. In terms of how to know where the electron is in the atom, this is sort of like part of the address. This is like what floor does the electron live on in a building. L is called the secondary quantum number. And the secondary quantum number has this range. It starts at 0, but again, after that it's positive integers, 0, 1, 2, 3, and it has an upper limit. Instead of going up to infinity, it has to stop at whatever 1 less than N is. Now, what's its meaning? Its meaning is what subshell is the electron in within a shell. So your shell is specified by your N value, and your N value limits the range of L. Every L number specifies a particular subshell. So if L is 0, that's one subshell. L is 1, that's another subshell. L is 2, that's another subshell within shell N. M sub L is called the magnetic quantum number. And the magnetic quantum number has this range. It starts at -L, and then it gets bigger until you get to -1, 0, +1, and then it can keep getting bigger, but it has to stop at +L. So it ranges by integers from -L to +L. Its meaning is, within a subshell, which orbital is the electron in? So in our address analogy, N is what floor, L is what suite within the floor, and M sub L is what particular room in the suite on the floor is the electron living in. The number of M sub L values that are possible for a particular L tells us how many orbitals are possible in that subshell. So if you have 3 different numbers, since each one specifies a different orbital, that means you have 3 orbitals in that subshell. So let's apply this to an actual shell. and see what we can learn about where the electrons are. This is called electron configuration. That's what we're working toward. In the first shell, where n is equal to 1, L could be 0 up to 1 less than n. Well, since 1 is n, 1 less than n is 0. So the only possible value of L is 0. What that means is there's only one subshell when n is 1. That subshell has a name, and it's called the S subshell. And that's mostly to avoid confusion, because the principal quantum number and the secondary quantum number both are mostly whole numbers. It's just a little confusing, so we use these letter codes. So if L is 0, we call that an S subshell. What's the possible value of M sub L? Well, remember, M sub L can range from negative L to positive L through integers, but since L is only 0, that means M sub L only has one value too, and that's 0. So here's what that means. There's only one orbital in an S subshell. Only one possible orbital. So that means you can only hold 2 electrons in there. That orbital is centered on the nucleus, and it's shaped kind of like a sphere. So if you think about it as a whole bunch of snapshots of an electron over a period of time, it's this picture here that has all these spots. If you think about it as a region with a boundary where the electron is likely to be found, this is what it would look like. And at the center, at the convergence of those 3 axes, there's the nucleus right in the middle there. So it's centered on the nucleus, and it's a spherically shaped region. Let's take a look at the second shell when n equals 2. If n equals 2, well then L has the possibility of being 0 or 1, because 1 is 2 minus 1. Well, the 0 subshell is an S subshell. There's a second subshell, however, so that means 2 subshells exist when n equals 2. The L equals 1 subshell is named a P subshell. That's the letter code. Well, if L can be 0, we know that M sub L can only be 0. So there's one subshell in the S, just like there was in the 1s. Well, if L is 0, then we know that M sub L can only be 0. We saw that in n equals 1. But if L is 1, then M sub L has this range. It can go from negative 1 up to positive 1 using integers. So there are 3 possible values of M sub L. So that means in a P subshell, there are 3 orbitals. And each one of these numbers, minus 1, 0, and plus 1, stands for a separate orbital. Their shape is kind of like a dumbbell-shaped structure. In the center is the nucleus. It's centered on the nucleus just like a S is, but it has 2 regions, 2 zones for this orbital. Thinking about it as a bunch of specks, we see this picture. But if we think about it as a region that's bounded in which the electron is most likely to be found, it looks like this picture here. And the X, Y, and Z axis cross each other on the nucleus. So here's what the 3 orbitals look like in their separate axes. And if you put them all together, that's the picture that you get. So they're 90 degrees from one another. So these are regions in space where the electron is likely to be found, centered on the nucleus. So we could ask ourselves, what's the maximum population of electrons in the second level? Well, if n is 2, then that means L can be 0, in which case we would have an M sub L that's equal to 0. So there's only one orbital in that subshell, and so that means there are 2 electrons there. But L can also equal 1 if you're in the second level. And in that case, we saw that M sub L could be negative 1, 0, and positive 1. So there are 3 possible orbitals. Each orbital can contain 2 electrons, and so that makes a total of 6. So if you sum these 2 together, that means the maximum population in the second level is 8. The maximum population in the first level is only 2, because there's only one orbital in an S sublevel. Look at the third shell. In the third shell, n equals 3, so that means L could possibly be 0, 1, or 2. Since there are 3 possible values of L, that means that there are 3 subshells in the third level. We've already looked at 0, that's the S sublevel, and at 1, which is the P sublevel. But now we have L equals 2. This is given the name D. Now, at S sublevel we saw had one orbital because M sub L could only range from 0 to 0. So that's one orbital. P has 3 orbitals because M sub L could range from -1 to +1, including 0. But if L equals 2, now we have this range for M sub L. M sub L can range from -2 to -1 to 0 to +1 to +2. So there are 5 possible values for M sub L. That means there are 5 orbitals in a D subshell. These are really funky looking, and they don't all look exactly the same. They have 4 lobes to them, most of them do, and they're organized off of the axes, mostly. And then we have this fifth shape that looks kind of like a donut with a p orbital imposed in it. But all of these things center on the nucleus. That X, Y, and Z axis goes right through the middle of the nucleus, and all of them would be kind of sitting on top of each other inside the atom. It's kind of complicated to visualize this in 3 dimensions, particularly if there are already S and P orbitals there. So what's the maximum population of electrons in the third shell? Well, we saw that when N is 3, L can be 0, 1, or 2. And a 0 or an S sublevel can contain 2 electrons. And then we saw that a P can contain 6 electrons. But sublevel 2, which is a D sublevel, can contain 10 electrons because it has 5 possible orbitals. So if you add up 6 and 2 and 10, you find out that the total number of electrons that could possibly fit in the third shell is going to be 18. Fourth shell. Well, if N is 4, then the values of L could be 0, 1, 2, or 3. But they have to stop at 3 because 3 is 1 less than 4. Since there are 4 L numbers, then that means there are 4 sublevels when N equals 4. The 0 is an S, the 1 is a P, we already saw that, the 2 is a D, and the number that, or the letter that's given to 3 is F. Now, if L is 3, M sub L has these possible values: -3, -2, -1, 0, +1, +2, and +3, which is 7 possible M sub L numbers. That means that there are 7 orbitals when you're in an F sublevel, or in other words, when L equals 3. 7 orbitals can contain 14 electrons. So what's the maximum population of electrons in the fourth shell? Well, in the fourth shell, when N is 4, L can be 0, 1, 2, or 3. That's an S sublevel, which can contain 2 electrons, plus a P sublevel, which can contain 6 electrons, plus a D sublevel, which can contain 10 electrons, plus an F sublevel. And F sublevels have 7 orbitals, so that means 14 electrons. So if you add up 14 and 6, that's 20, and 10 more is 30, and then 2 more is 32. That tells you that you can put 32 electrons in the fourth. So as atoms get bigger and bigger, they need more and more of these shells to fit all their electrons in. The value of N can be infinite. Remember, it ranges from 1 to 2 to 3, and it could go all the way up to infinity. But for most practical purposes, in this class at least, this is all we're going to have to think about, is usually about 4 or 5 sublevels in about 5 or 6 main shells. So how do you know where the electrons are in a particular atom? Well, to do that, we use something called the Aufbau principle. Aufbau is German for building up. And that's literally what we do. We think about building an atom from the lowest energy level up. So electrons in an atom occupy the subshells that have the smallest energy, and then once those are full, they build up from there. So we're going to build a graph here that gives us an idea of how this works. This graph graphs energy on the y-axis. So energy is increasing as we go up the side. The very lowest shell is the 1 subshell, and it only has 1 sublevel, and so we see one single line here. The next level is N equals 2, but that's split. because if n is 2, then there are 2 values of L. That means there are 2 sublevels. So there's a 2s and a 2p. 2s is slightly lower energy, 2p is slightly higher energy. The next level is 3, but 3 is split 3 ways because there are 3 possible values of L. So there's a 3s subshell, a 3p subshell, and a 3d subshell. Now, as electrons enter an atom on this chart, they enter the lowest possible level that they can find, and then they move up only after that level is full. So let's think about hydrogen. How many electrons does hydrogen have? Well, if you look on the periodic table, you see that hydrogen is element number 1. That means 1 proton. But in a neutral atom of hydrogen, that also means 1 electron. Where does that electron go? I'm going to use an X to model an electron. So that X, I'm going to put right there. It's on the first level, the 1s subshell. What about helium? Well, helium is element number 2, so that means a neutral atom of helium would have 2 electrons. So if I put my X's in, they're both going to go on that 1s line, because a 1s subshell has 1 orbital, and 1 orbital can contain 2 electrons. Lithium. Well, lithium has 3 electrons because it's element number 3. The first 2 have to go in this lowest sublevel, but then it's full because 1 only has an s sublevel. An s sublevel has only 1 orbital, and 1 orbital can contain only 2 electrons. So that's full. The next electron has to go in the 2s, which is the next sublevel. Let's look at carbon. Carbon is element number 6. Well, I have an s sublevel here, and that can contain 2 electrons. This s can also contain 2 electrons. And 2 plus 2 is 4, so that's not going to give me enough room for all the electrons in carbon. I'll have to jump to the next level, and this is a p sublevel. P's can contain up to 6. So my first 2 electrons go there. My next 2 electrons go there, and the remaining 2 electrons are going to go at the p sublevel. Now, if we keep going up through here, we see that once that got full, once we had 6 x's on that line, we'd have to move to the 3s, which can contain 2, like all s's. Then we'd have to go to 3p, which can contain 6. And then when that was full, we'd have to go to 3d, which could contain up to 10. Well, we're going to use this idea of the alpha principle in the next video to show you 4 different ways that you can represent what's going on with the electrons in atoms. And that turns out to be really important because in chemistry, almost all the action happens with the electrons. And it's actually not even with all the electrons. So we have several shorthand kind of ways of describing the atom to give us ways to predict how chemical change is going to happen when 2 different kinds of atoms get together.